let's now generalize the idea of a tree and talk about graphs. So trees, they're really great for representing these strict hierarchical relationships, but not every relationship is hierarchical. So for example, consider this schematic picture of the Paris metro system. If we look at stations A and B, there are two different ways of getting from A to B. I can either go along this bottom path or this top path, or take some other really strange path to get to B. This, as a result, it has cycles in it. It has two different ways of getting from A to B. It's not a hierarchical relationship where there's one boss and those have children and so forth. It's more democratic. In fact, hierarchical relationships, they could be a little rare. So if you think about the family tree of all humans, it is not in fact a tree, because somewhere, all of our ancestry converges, and so there's multiple paths to get back from you to some earlier people. Because in general, whenever you have two parents of a child, they are maybe some number of cousinness relationships away. I don't know, 10th, 15th cousins, whatever. But, if you have babies, whatever happens, the person that you're having kids with is your somethingeth cousin. I don't know what number it is, but it's going to be some big number. So if we want to capture this much richer set of possible relationships, we need something else. For example, and that brings us to the idea of a graph. So a tree, we already saw this exact slide. In a tree, you have to have exactly one path between any two nodes. So if you have two paths or no paths between a certain node, or between a certain pair of nodes, that is not a tree. And so a graph is just the same thing where we remove this constraint. So a graph consists of a set of nodes and a set of 0 or more edges, each of which connects two nodes. So all four of these structures here are graphs. It's just a generalization of a tree. Okay. So question. Let's take the BART graph, circa 2019, and ask ourselves, is it a tree? It's a graph. It helps you see all the stations out there. Is it a tree? Okay, so it is not a tree because it has a cycle. You can go from San Bruno to Millbrae to San Francisco back to San Bruno. Okay. So not a tree, but other than that, it's almost a tree. Okay. All right, so just a little fun question. So a simple graph, I just want to introduce some more terminology. It's going to be a lot in this video. A simple graph is a graph with no edges that connect a vertex to itself, so you can't have loops. And it also has no edges that no two edges that connect the same vertices. So there's no parallel edges. So the green graph is simple, but these pink graphs are not simple. Now, I will note that simple graphs are so much more common in real-world use and in algorithms that I'm actually just going to use the term graph as a shorthand for simple graph. So in 61B, when I say graph, I mean simple graph. So unless we explicitly say otherwise, you should assume you never have multiple edges or parallel edges, and you should also assume you never have loops, that is, edges to them that a node has to itself. More terminology. So graphs, since they're used to model so many different things out there, we often distinguish between what is known as a directed graph and an undirected graph. So in a directed graph, each edge has a directionality, and this could be used, for example, to model one-way streets. We also distinguish graphs that are acyclic from cyclic. So an acyclic graph is, a tree. It's a graph where there's no cycles, whereas a cyclic graph, there are multiple paths. Now I should be a little careful there, because you can have an acyclic graph that is not a tree because it has some nodes that are disconnected. All right, and so here, because remember there's two ways to make a graph, there's two ways that a graph can be not a tree. It can either have cycles or it can have disconnected nodes. All right, and then the last thing I'll mention is that often we'll label our edges with some values. And this might represent, for example, the length of a road, where each node is an intersection. But wait, there's more. So this is a figure from our optional algorithms textbook, and I just want to talk through these terms because we'll be using them lots over the coming lectures. So a graph, it's a set of vertices, also known as nodes. I will use those terms interchangeably without even thinking. It has also a set of edges, and you can think of each edge as a pair of vertices. The vertices that have an edge between them are considered adjacent, and optionally, vertices or even edges can have labels or sometimes called weights. A path we will define as a sequence of vertices connected by edges. So for example, here's a path of length 4, 1, 2, 3, 4. And a cycle will be a path whose first and last vertices are the same. So here is a cycle. So if I think of this here, the path from here to itself, we have 1, 2, 3, 4, 5. Okay. So this is a cycle of length 5. A graph that contains at least one cycle is called cyclic, and if it has no cycles, it's called acyclic. And then we'll say two vertices are connected if there's a path between them. And if all vertices are connected, the entire graph is considered to be connected. Now, not in this list here, but shown in this figure, is that any subgraph that has all of the vertices connected is known as a connected component, and we saw that phrase when we were talking about disjoint sets earlier. Okay. I also don't mention here the idea of degree, but a vertex's degree is how many edges are touching it. So there's some graph terminology. Okay, so let's reflect just a little bit on some graphs. Let's start with the Paris Metro. This is a schematic map. That is, it's not actually showing the names of the stations, and the colors don't actually correspond to the names of the lines. But the graph here, if we look at it, it is undirected. You can go either way between stations. It is connected, so there's no stations that you cannot reach from any other. Like that is, all stations are reachable from every other. And it is cyclic. That is, we can go in circles, so it's not a tree. And it's vertex labeled because each has a color. And what these colors mean, I'm not quite sure. So that's an example of a graph and in terms of these definitions we've given. Another example here is a directed graph. This is a graph known as WordNet, which is a graph of all nouns in the English language, letting you know a bunch of hyponym relationships. I think I mentioned this in an earlier lecture briefly. So for example, demotion is a type of change, and change is a type of action, and action is a type of human action, human activity, and that is a type of event. Okay. So this approach, or this tree here, I should note it is not, this graph here is not a tree. For example, there are two paths from group action up to event. I can either go straight to event, or I can go through this intermediate node. I will not discuss this graph in any detail, so you might be wondering why there's these two paths. What does this mean? Why is miracle hanging right off of event? Not our problem in this class, but hey, kind of fun. All right, so what we'll do next is, now that we understand what graphs are, we'll start thinking about the really rich number of problems that are out there and types of problems that we can try and solve with graphs.